Hello, everyone. Thank you for joining us for the second session of the ARSET webinar series, Remote Sensing of Land Indicators of Sustainable Development Goal 15. My name is Cindy Schmidt, and I will be your instructor today. Before I get started, I wanted to let you know if any of you are having problems with hearing with the audio, you might try using Chrome. Some people in the earlier session were saying when they switched their web browser from whatever they were using to Chrome, it seemed to work a little better. So I thought I'd give you a heads up on that in case you are having problems hearing anything. For this course, we will have 2 sessions each day. Session A was already from 1 to 2:30 p.m. Eastern Time, and session B, which is this session, is from 10 to 11:30 p.m. Eastern Time. Please make sure that you've only been signed up for one of these session times. We've created 2 sessions mainly to reach out to our broader international audience. We'll have lectures followed by a short Q&A session. You can find all the course materials at the website listed here, our ARSET website. This includes past recordings, the presentation materials, and the link to the homework. We will also eventually have each of our presentation materials available in Spanish. If there are any additional questions, you can email me or my colleague Amber McCullum at the email addresses listed below. We will have one homework assignment after all 3 sessions, which will be submitted through Google Forms. The link will be available after the final session, so after the session tomorrow on the website, and we will post it in the chat box during the final session. To receive credit for homework, you must submit all answers via Google Forms by July 6th. To receive a certificate of completion, you must attend all live webinars and complete the homework. It takes some time to process these certificates, so you can expect to receive them about 3 months after the completion of the course. There is one prerequisite for this course. First, you should know and understand the fundamentals of remote sensing. You can watch our on-demand course listed above, which includes 2 one-hour recorded webinars that you can watch on your own time. As I mentioned previously, you can access all the course materials on the ARSET website. Each session, you will be able to find a PDF of the presentation in both English and Spanish. The Spanish versions will be available at a later date, hopefully soon. A link to view the recording of each webinar session, and the link to the Google form for homework submission at the end of the 3rd session tomorrow. Please note that in order to view the webinar recordings, you must register. This helps us keep track of who is viewing them. Once you register, you will be automatically taken to view the recording. So here's an overview of the course agenda. Last week, Amber discussed, and she did an overview of SDG Goal 15. And this week, I will be discussing SDG Target 15.1. And then tomorrow, we will be discussing SDG Target 15.3. Our agenda today includes discussing SDG Target 15.1 and Indicator 15.1.1. I will then discuss some existing land cover data that you can access, as well as how to access them. Then I will discuss different methods to create a land cover classification from satellite imagery. Lastly, Amber McCullum will demonstrate how to access and visualize MODIS land cover data. So first, I'll discuss Target 15.1, followed by available land cover data and tools. SDG Target 15.1 says by 2020, ensure the conservation, restoration, and sustainable use of terrestrial and inland freshwater ecosystems and their services. In particular, forests, wetlands, mountains, and drylands in line with obligations under international agreements. This week, we will be focusing on indicator 15.1.1, which is forest area as a proportion of total land area. Forests fulfill a number of functions that are vital to humanity, including the provision of goods and services such as habitat for biodiversity, carbon sequestration, coastal protection, and soil and water conservation. Indicator 15.1.1 provides a measure of the relative extent of forest in a country. The availability of accurate data on a country's forest area is a key element for forest policy and planning within the context of sustainable development. Changes in forest area reflect the demand for land for other uses and may help identify unsustainable practices in the forestry and agriculture sector. This indicator may be used as a rough proxy for the extent to which the forests in a country are being conserved or restored, but it is only partly a measure for the extent to which they are sustainably managed. According to the FAO definitions, forest is land spanning more than 0.5 hectares with trees higher than 5 meters and a canopy cover of more than 10%. Or trees able to reach these thresholds in situ. It does not include land that is predominantly under agriculture or urban land use. There are more specific definitions, including areas with young trees that have not yet reached, but which are expected to reach a canopy cover of at least 10%, and tree height of 5 meters or more. It also includes areas with mangroves in tidal zones, as well as rubber wood, cork oak, and Christmas tree plantations, but excludes tree stands in agricultural production systems such as fruit tree plantations, oil palm plantations, olive orchards, and other agroforestry systems when crops are grown under tree cover. To report forest area, countries are asked to assign a tier level 1, 2, or 3, indicating the level of detail of data sources used for reporting. Tier 3 is the highest level of detail, and estimates can include recent data from national forest inventories or remote sensing with ground validation. Tier 2 are estimates older than 10 years from national forest inventories or land cover mapping from remote sensing. There are several existing data sets to derive forest and land cover data with varying levels of spatial and temporal resolution. In this webinar, I will describe the data sets listed here. Many people think of Global Forest Watch for the forest disturbance data that it has, but it also has other information such as tree cover, intact forest landscapes, above ground live woody biomass density, mangrove forest, and land cover. The tree cover data have a 30-meter spatial resolution from the year 2000. It includes all vegetation taller than 5 meters in height and categorizes the tree density in terms of percent cover. You can adjust the minimum canopy density for tree cover in the interactive map that you can see on the right. The intact forest landscapes data includes the world's last remaining unfragmented forest landscapes, large enough to retain all native biodiversity and showing no signs of human alteration as of the year 2013. These landscapes are at least 50,000 hectares in size and have a minimum width of 10 kilometers. The global land cover data set uses imagery from 2009 and has a spatial resolution of 300 meters. These data were developed as a part of the European Space Agency initiative called Globe Cover, which I will describe in a minute. The Food and Agriculture Organization has been monitoring the world's forests at 5 to 10-year intervals since 1946. These assessments are now produced every 5 years. The assessment is based on two primary sources of data: country reports prepared by national correspondents and remote sensing that is conducted by FAO and national and regional partners. The 2010 Forest Resource Assessment Global Remote Sensing Survey was the first comprehensive global survey on forest land use and change dynamics over time. The survey was implemented by FAO in collaboration with the EC Joint Research Center and other partners. Key outputs include a synthesis document called "How Are the World's Forests Changing?", as well as country reports, which contain the documentation of references and data used for reporting to the Forest Resource Assessment 2015. The Forest Resource Assessment 2015 data are available in several different forms. In addition, the maps can be downloaded as images, and the data can be visualized through an online platform called the Forest Land Use Data Explorer. I will show you some features of this tool next. The Forest Land Use Data Explorer is an online platform intended to make it easy to access and analyze forest land use and forest resource data. Most of the forest land use and resource data come from the Global Resources Assessment 2015. This tool also provides access to data sets that relate to forests, including agriculture, rangelands, demographics, market prices, land use classifications, and maps. You can download the data yourself or analyze data with a few tools. Here's some of the options available in the Forest Land Use Data Explorer. You can filter the data by different types of forest area, such as deforestation, which is human-induced, planted forest, natural forest, mangrove forest, etc. You can specify the year ranging from 1990 to 2015. You can also specify the area of the world you're interested in, such as subtropical, tropical, or temperate. You can specify incomes ranging from low to high. And lastly, you can specify a subregion, such as the Caribbean, Central America, Europe, North America, etc. The data are provided by country and includes maps as well as tabular data. The FAO Global Land Cover Share database provides a set of major thematic land cover layers resulting from a combination of best available high-resolution national, regional, and or subnational land cover databases produced at a resolution of 1 kilometer. The data includes 11 land cover classes and are distributed in separate layers in GeoTIFF format through the FAO Geo Network portal. The FAO also has national and regional land cover data sets for many countries in Africa and the Himalayas. So I'm going to just stop here for a second, and I noticed that some people are having problems with the audio. The primary issue with audio if you're having problems is either try a different web browser, or it's your bandwidth, it's the slow internet connection. There's not a lot we can do about that, unfortunately. So I apologize if you're having some audio issues. What I recommend if the audio issues continue is that you log off and then access our recording a little bit later. That may be the best way you're going to be able to do it, because there's nothing on this end that we can do to solve the audio issues that are on your end. So I apologize for that. And thank you. Some of you are getting good audio, so I'll continue. Through its climate change initiative, the European Space Agency produces annual global land cover time series data from 1992 to 2015 at a spatial resolution of 300 meters. The effort was supported by processing data from different satellite missions, including NOAA AVHRR, SPOT, NVSAT, and PROBA-V. The data include 22 land cover classes based on the UN land cover classification system. You can visualize and download these data using the CCI land cover viewer. So this is what the CCI land cover viewer looks like. On the left, you can see the various land cover types, including percent tree cover. You can select the year you want on the top of the screen, and you can also get graphs that include greenness seasonality, snow seasonality, and burned area seasonality. You can download the data using the button on the top right. You can either do a pixel-based extraction in a .csv format, or you can download the raster data in GIS-ready formats. In 2010, China launched the Global Land 30 Mapping Project, producing a land cover map with 10 classes for 2000 and 2010 at 30 meter spatial resolution. The data can be visualized at the website listed here and can also be downloaded from the same website. The MODIS yearly land cover product incorporates 5 different classification systems that describe land cover properties derived from observations spanning a year. The primary classification scheme identifies 17 classes defined by the International Biosphere Program, which includes 11 natural vegetation classes, 3 developed land classes, and 3 non-vegetated land classes. The data have spatial resolution of 500 meters. Currently, the MODIS version 5 processing has ended, so the land cover product is currently only available from 2001 to 2013. The new suite of version 6 land cover products are expected to be complete by the end of 2017. You can download these products from NASA's Earth Data website. This image shows the MODIS Global Land Cover product with the 17 land cover classes. Note that it has 5 different classes for the different types of forest. You can download the MODIS Land Cover product through NASA's Earth Data web portal, pictured here. Amber McCullum will be demonstrating how to do that later in this session. Next, I will discuss how you can do your own land cover classification from satellite imagery. Reliable land cover information is important for evaluating progress for several SDG targets, but it is essential for SDG 15.1.1 and determining baseline conditions for indicator 15.3.1, which we will discuss tomorrow. The first thing you need to consider when doing your own land cover classification is the scheme you want to use, which will be used to categorize and label land cover. It is important to spend some time designing a classification scheme because it's critical to derive useful information from the satellite imagery. Remember that when you use satellite imagery to map land cover, you are identifying land cover through its unique spectral reflectance. You are mapping land cover, not land use. So some classes may be very difficult to distinguish from each other. There are some basic rules when developing a classification scheme. The scheme must be exhaustive. In other words, all land cover in the image must be included. The classes must be mutually exclusive, so there is no overlap between the classes. Lastly, it must be based on what can be interpreted from the imagery. For example, if you create an understory class, you will not be able to see that in the image because you can't see beneath the tree canopy using satellite imagery. In addition, schemes should have different levels, such as dividing a forest class into hardwood and softwood. The classes have to be based on measurable land cover characteristics such as size class or percent canopy cover. You should avoid subjective, non-measurable classes such as old growth because these types of classes often do not have unique spectral characteristics. An example of a good classification scheme might include the percent canopy cover forested area such as described here. Sometimes you can develop classification schemes that include different forest types, but only if those forest types are spectrally distinct. There are some new classification techniques that enable you to distinguish between some land cover types based on including other data such as elevation and aspect. There are different types of schemes such as those listed here. These classes can typically be derived from moderate resolution imagery such as Landsat and the Sentinel instruments. The forest non-forest map is typically used for basic trend analysis and can be used as the basis for other products. This type of map shows the extent of all forest types within a country. The minimum mapping unit, or the smallest area to be mapped for all maps, should be less than half a hectare. The temporal frequency that the maps have should be updated is annually. The forest stratification map identifies forest types with common biomass densities. This ultimately provides more accurate carbon estimates, which might be useful for addressing indicator 15.3.1. The suggested primary stratification is primary forest, modified natural forest, and planted forest, as long as they have different densities and you can spectrally distinguish them. The all land use categories map can be used for national baseline mapping. A good example is the UN FAO land cover classification system. It is important that you understand the difference between a spectral class and an informational class. A spectral class is a group of pixels that are spectrally similar. An informational class is a land cover class of interest. Image classification is the process of assembling groups of similar pixels into classes that are associated with informational land cover classes. Image classification has been used to transform the satellite image of Panama on the left to the land cover map on the right. Just as a refresher, each object on the Earth's surface has its own spectral signature. In this simple example, vegetation characteristically absorbs electromagnetic radiation in the red wavelengths, so where it says band 3, but reflects in the near infrared, where it says band 4. Soil, on the other hand, reflects higher radiation in the infrared wavelengths than the visible wavelengths. We can look at these objects a little differently if we plot one band against another. In this case, plotting Landsat band 3, and this is from Landsat 5 or 7. Landsat band 8 is a little bit different. It'll be band 4, which is the red band, versus Landsat band 4, or the near infrared band, results in water in the lower left with low reflectance in both bands, vegetation on the lower right because it has low reflectance in the red band but high in the near infrared band, and dry soil with higher reflectance in the red band but somewhere in between water and vegetation for the near infrared band. So the software uses this information to distinguish between the different land cover types. If we go back and just focus on the vegetation spectral signature, but plot several types of vegetation, you will notice that although the general trend is the same, there is some variation between the different vegetation types. The key to understanding how to do a land cover classification is how to deal with this variability. Looking at the spectral signatures between vegetation and soil, you can see that it is easy to distinguish between vegetation and soil, but it's much more difficult to distinguish within these broad classes. If you translate the plot on the left to the plot on the right, you will see that some of the vegetation pixels are spread out, but some are quite close together. This is similar for the soil pixels. To make it even more confusing, we have been looking at spectral plots in 2 dimensions using only 2 image bands. Most of the time, you will be using more than 2 bands for classifying imagery, so the spectral plots become much more complicated. On the right, you can see what a spectral plot in 3 bands might look like. You can imagine how difficult it is to determine the pixel characteristics of Landcover types in 5 or 6 bands, but fortunately, the software can do that for us. The process of image classification includes defining the boundaries of classes in n-dimensional space, or n, the number of bands, using statistics of groups of pixels that represent Landcover classes. Each group of pixels can be characterized by a variety of statistics, including the mean, minimum value, maximum value, and standard deviation. The standard deviation is important because it tells you how tight or how spread out that group of pixels is. So the image on the right shows you the circles, which are specific classes, but within those classes, you can see how much those points are spread out, and that tells you how much variation there is within that one class. In image classification, then you assign a class name to the groups of pixels in the spectral plot, and all the pixels in that image fall within those class statistics are given those labels. For example, you may identify a few vegetation pixels in your image, but since you can't easily identify all the vegetation pixels, the computer looks at all the pixels in the image that are similar to those pixels that you identified and labels those pixels as vegetation. There are many different ways to classify imagery, but almost all can be categorized into 2 approaches: pixel-based and object-based. In pixel-based approaches, each pixel is grouped into a spectrally similar class. These approaches are most useful where there are multiple changes in land use within a short period of time, and they are best suited when there is wall-to-wall data coverage and time series consistency at the pixel level is required. Object-based approaches partition an image into groups of pixels that are spectrally similar and spatially adjacent. Boundaries of pixel groups delineate ground objects in much the same way a human analyst would do based on its shape, tone, and texture. This process is called segmentation. These kinds of images can be easier for an analyst to interpret. This approach is also used on radar imagery to reduce speckle. It is especially useful for high spatial resolution imagery because pixel-based approaches tend to be very noisy. The images below show the visual differences between the 2 approaches. On the left is the pixel-based approach, and on the right, you can see that same image that has been segmented and classified. It produces a much smoother image. In this webinar, we will describe in more detail pixel-based approaches to image classification. There are many different ways to create land cover maps. 2 common methods include supervised and unsupervised. The supervised method can use either a pixel-based approach or an object-based approach. The unsupervised method uses a pixel-based approach. The supervised method uses user-defined areas of known land cover types that are called training areas. These areas are then used to define the statistical parameters of classification algorithms. The algorithm then automatically identifies and labels all pixels or segments that are statistically similar to the training data. In the unsupervised method, a classification algorithm assigns each pixel into one of a number of user-specified classes. Then interpreters assign each of the pixel groupings a value corresponding to a land cover class. This shows a little more detail about the supervised methods. The spectral signatures from the training areas are used to categorize each pixel or each segment in the image, resulting in the entire image being classified. For those of you that are interested in learning more about how to do image classification using the supervised approach, I recommend that you look at the webinar. We did an advanced webinar in January using QGIS open source software to do the supervised approach. So we went into much more detail about how you do this, and then there's some exercises associated with the webinar that we did. So you can do some hands-on types of things. So I highly recommend that if you're interested. In supervised and unsupervised methods, a classification algorithm is used to actually classify the image. For example, in QGIS, which is the software that I just mentioned, which is an open source geospatial software, it uses 3 different types of algorithms that are listed here. In addition to supervised and unsupervised, there are other classification methods, including decision tree and random forest. This decision tree, also known as classification and regression tree or CART, uses training data to develop a tree-like set of rules to determine the class for certain combinations of input data. Then every pixel is labeled with a class utilizing the decision rules of the classification tree. Random forest creates many decision trees based on predictor variables. A decision tree classification approach uses the spectral information from the image, but also includes additional data that may be useful in identifying land cover types, particularly for those classes that can be spectrally confused. In this example, shrub and grassland are separated using pixel values from Landsat band 4 and also NDVI values as well as aspect values. The idea is that for higher NDVI values, shrubs tend to occur on aspects greater than 180 and grasslands tend to occur on slopes with aspects less than 180. Although it may take some time to develop the rules for a land cover classification, once the rules are developed, classification is fast. Random forest is another approach to mapping land cover. This approach calculates land cover or percent tree cover by creating many different decision trees and applying each pixel in an image to each of the trees. Inputs for this approach include training or reference data, so you need data from the ground or some other reference, and predictor variables, including the image bands and other topographic and or bioclimatic variables. Other predictor values can be derived, such as NDVI or other image transformations like tassel cap. The training data are used to develop the decision trees. Hundreds of these trees are created randomly and built for the desired land cover classes to create a random forest model. This model is then used to classify the whole image. The decision tree on the right is just one of hundreds that are developed using this approach. In summary, satellite imagery can be used to get information about forest area for indicator 15.1.1. There are many existing land cover and forest maps derived from satellite imagery, or you can create your own land cover map using a classification approach of your choice. Next, Amber McCullum will be doing demonstrations of how to access and visualize MODIS land cover data. So bear with us for a few seconds here while we switch over to Amber's computer.
All right, thank you, Cindy. So we will get started with our demo here today. For this demo, we will show you how to download MODIS land cover data from the NASA Earth Data Search. We will then open up the MODIS land cover data in the geospatial software QGIS. This is a freely available open source software similar to ArcGIS that can be used for mapping. Next week, we will examine changes in land cover using MODIS and land cover data from Global Forest Watch. So first, let's go to the Earth Data website here and click on Data Discovery and then Earth Data Search. First, you'll be asked to take an introductory tour, which I recommend. You can do this by clicking on Start Tour. However, I will not show you this here. If you're logged in, you will see the Earth Data login along the top. If you click on it, you'll be redirected to create an account. Accounts are free and anyone can sign up. So because I have already logged in and it remembered me, so it takes me back to the Earth Data. For this demo, we are interested in finding MODIS Landcover data. So in the search, we can type in MODIS Landcover MCD. We can type very slowly. When you type in the name up here, you can see that the collections automatically change here at the bottom. So once you type in the name of whatever it is you're interested in, the granules that load at the bottom. MCD12Q is the short name for this, this product. So once you type that in, you will see the data set that we're interested in, MODIS Terra Aqua Landcover Type Yearly L3 Global 500 meters sinusoidal grid, shown here. So if you click on these data, you can see all of the available granules listed here. So let's take a step back and get all the information about this data type. So we can also view the MODIS Landcover data information page on the LPDAC. So if we just Google MODIS LPDAC Landcover, the first option that comes up will be the information page. So if you click on this here, we can see information about this product. If we scroll down, we can see overview, layers, and links. If we click on the overview option, we can see that the Landcover type product contains 5 classification schemes, which describe Landcover properties derived from observation spanning a year's input of the Terra and Aqua MODIS data. So there are various types. And for this demo, we are interested in the Landcover type 1, shown right here. So if we click on layers, we can see the naming convention for each Landcover class. For IGBP, or type 1, each cover type has these specific categories. So the data will be given these values based on the class assigned. There's also the University of Maryland, or UMD, classification. That's a very useful one to use. So we'll use this page as reference later on. So for now, let's go back to the Earth data search. We can use these temporal and spatial filters at the top to refine our search. So for this demo, we're going to look at land cover changes in Malaysia. So let's navigate to Southeastern Asia here. You can scroll over and zoom into the region using your mouse, or you can use the plus and minus signs on the sides of the tool here. So once we've zoomed into this region in this portion of Malaysia, north of Indonesia, we can then use the spatial filter and draw a rectangle. And once we draw this rectangle, the filter will automatically be applied to our search. And then you'll see this green outline that indicates the MODIS swath for this region. So now if you take a look at the data here on the bottom, you will see there's a data collection for each year for this swath, starting with 2013 and then going all of the way to 2001. And this is the length of time the MODIS land cover data are available. You could also do a temporal search if you're interested in only one of those years. But for this example, we're interested in each yearly data set. For our demo next week, we'll look at differences in the yearly data. So if we want to download all of these data, we will come down to the bottom here and click on this green Download Data button. Once this loads, you'll have options for selecting your data. we can see once it loads, we can see 13 granules and one for each year. For the service option, we will select the customized product that's already checked here. This allows us to select specific parameters for the data. Make sure that your email address is correct here as well. We will keep the reformat option listed as GeoTIFF, and we do not need to do any kind of spatial subsetting because we want the entire swath. You can then select different reprojection options shown here, but I'm going to stick with the geographic. You could also select things like UTM. We will also keep the geographic parameters as defaults. These things such as the datum and the resample dimension and the interpolation method. We'll just keep those as the default. Now we can also select specific bands or layers that we want to download in this band subsetting option here. For this example, I'm only going to select classification type 1. So I can use this drop down here to then uncheck all of the layers that I don't want. And we'll just keep the type 1 land cover layers. So then if you scroll down and click on continue, if you're logged in, your information should be shown here. Just double check that that's all correct. Then if you click submit, the process will run. You will receive an email from LPDAC saying they received your order and when the order is complete. If you keep this window open while the processing occurs, you'll be given a link to a zipped folder with these files. So I've already ran this, and I'm showing this site here where you can see the zipped folder right here, and then you can download all of these files at once. And this may take a while depending on your network speed. Once the data have downloaded, you can save the folder to the file where you can reference it later on. In order to view the data, we're going to use an example of QGIS. So here I already have a QGIS map open. You can find information on how to download this on the course website. We can use the Add Raster button here, and then we can navigate to our file structure, and you'll see some kind of naming convention similar to this. Within each folder are the data files for each year. For example, if I click on this first folder, I can see all the file names. Notice that this is the 2001 data layer, and you can tell this by the 2001 in the name. You can find more information about the MODIS naming conventions in our fundamentals course that was a prerequisite for this course. So if we'd like to choose the Landcover type1.tiff file, this is what we want. So we'll click on open. You will notice that the file looks totally black, but that's okay. We just need to reclassify it. So if we right click on the file in the side panel, we can then choose properties and then go to style, and you can change the render type from single band gray to single band pseudocolor. Remember that you can refer back to the class types on the LPDAC website that we looked at earlier to get these classifications. So let's go back there for a moment. So you can see back here that there are 19 classes for the type 1. So we have things like water, evergreen needle-leaf forest, and mixed forest. Within your QGIS map file, you can then create these categories. You will need to do this manually, at least for the first file. So let's go back to our QGIS map. If you, again, right-click and go to Properties, and then choose the single band pseudocolor, and then come over to the color map and choose equal interval mode here, and 19 classes. Then click on Classify. You will then need to change the values and the labels to match what we just looked at on that LPDAC website. So we'll just do the first one here. You will need to click on each class and change the value to match those on the website. So for water, the first value was 0. We can type in water, and then we can change the color to blue. If we click on apply and then OK at the bottom here, we can see that the blue has been applied to our map. So you can do this, once you've decided on the categories, you'll need to do the same thing for each of those categories that are the same as the LPDOC website. So you'll need to refer back to that website. I've already actually saved all the categories, and once you do that, you can export the color map to file, and then you can load the color map that you've created the first time. So I'm just going to navigate back here to my Landcover colors map that I created and click on open. So now you can see that I've changed all these colors and the labels and the values to match those on LPDOC. Then you click apply and OK, and you can see now the colors are reflected in the map. The last thing we'll do here is just add a little Google map to orient us. So if you go along the top to web, and then open layers plugin, and then Google Maps and Google Physical, you will see the region come up in Google Maps. You can then move the Google Maps base layer below your file. You can also go into your file properties, again by right-clicking and going into properties, and then going to transparency, and we can just move that transparency on over to 20%. And then you can click OK and apply and OK, and you can get some reference as to where you are. You can also click these layers on and off to go back and forth. If we want to double check our Landcover category, you can also use this information tool here. Then we can click anywhere on the map and see what the category of that region is. So for example, the majority of our region is evergreen broadleaf forest, or category 2, shown here. We could also zoom in to different regions, such as this region here, and identify different Landcover classes within this map. So if we click here, we can see that's value 13, and that corresponds to an urban area. We could also click on this red and see that that's value 2, and that corresponds to croplands. So this ends our demo for today. In the next session, we will look at similar types of data from the Global Forest Watch and then compare those data with our MODIS Landcover data. So I am just now going to close this out really quickly and shift gears back over to Cindy, and then we have a few minutes for any kinds of Q&A session.
All right, everyone, as my screen slowly comes up here, hopefully at this point you'll see the contacts listed there. So my email, you'll see my email and then Amber's email. So if you have any questions about this or actually any other of the ARSET webinars, we're happy to help you with that. If you have general ARSET questions, you can contact Anna Prados, who is the lead for ARSET, at the email address listed here. And of course, if you want to access any of our previous webinars, including the supervised classification one, you can go to our website that is listed here. So we want to thank everyone for attending today. I guess today for some of you, tonight for me and Amber. It's kind of different times all over, but we're happy that you joined us today, and hopefully you can join our third and last session tomorrow at the same time. And at this point, we're happy to answer any questions that you might have. We apologize for the sound issues. It usually just comes to bandwidth, unfortunately. So these kinds of webinars take up a lot of bandwidth. So if there's intermittent internet or low bandwidth issues, then unfortunately the audio problems that it's really hard to deal with those audio problems. So apologies for that. One question I'd like to ask those of you who are still online is if we were to do an advanced webinar, so that's one where you would actually use software to do some processing and we'd have some exercises, would you be interested in accuracy assessment, which we haven't discussed here today, but I know it's an important part of land cover classification. So would you be interested in accuracy assessment? Would you be interested in object-oriented land cover classification, or anything else? If there are other kinds of trainings that you're interested in, especially if you want to use some specific software, just let us know. We'd like to hear from all of you about what's of use to you. And I'll take a look at some of the questions here. Here's a good question from Sylvia. Which definition is appropriate for land use cover classification? Is it the FAO or the IPCC definition? So I think that's really dependent on each location or each country. Everyone sort of uses different classifications. I know that the FAO land cover classification is used very widely. So it's really kind of dependent on what your needs are. So that's a very hard question to answer. Is there a fixed classification for classes of MODIS image? Yes. So the MODIS image land cover classification classes do not change. They're the same. So you can compare them across years. And that's kind of the point of doing the same classes over many years. And here's one request for object-oriented land cover classification. Excellent. So here's a question, which one is best, ERDAS Imagine or QGIS? So for those of you that don't know, ERDAS Imagine is an image processing software, one of several actually, there's a few out there, but they cost money. So ERDAS Imagine has some really great features. It's pretty easy to learn. QGIS is open source, so it's free. It's right now QGIS is really has a lot of great sort of GIS capabilities, but the raster processing capabilities are improving all the time because it has a connection with GRASS, which is a raster processing package as well. So QGIS is probably not quite as easy to use because it is open source and a lot of people write modules, but it's free. So there's some trade-offs there. Okay, there's some more requests for object-oriented and accuracy assessment. Also a webinar on R and random forest. Yes, that would be really fun to do. Object-oriented and tree, the decision tree classification, great. We'd love to hear from you about that. How do we define a cocoa farm? A forest or a crop? That's a really good question, Sylvia. I think my guess is that it would be a crop, but I'm probably not the right person to answer that question. So maybe that's something we can try to investigate for you and get back to you. Open source like R and Python. Then there's some accuracy assessment. Yes, I think we probably will do at least one on accuracy assessment next year. Object-oriented classification. So a lot of requests for that. That's great. Great to get your feedback. So here's a question about accuracy of the data. One thing we didn't address in these webinars, just primarily because we didn't have time, is accuracy assessment and how you do that. So there isn't time here to really discuss accuracy assessment. So I think my guess is, I think what we're going to do for next year, or sometime after October 1st of this year, is do a whole webinar series on accuracy assessment and show you how to do that. Yeah, so somebody asked about other open source software for raster processing, which, alternatives to ERDAS and ENVI, that's more advanced and user-friendly. Honestly, QGIS, I think, is one of the most user-friendly open source software that I've seen. Other people use some packages in R, but I don't think that's nearly as friendly as QGIS. So for open source software, I think that's probably the best way to go. There is another free software package called Multispec, but it's not open source, so you can't have added packages to it like you can. It has sort of limited capabilities, although it's very easy to use. So it's just called Multispec, and maybe we can send you all, or at least respond to you here about what the website is for looking at Multispec. So here's a great question. Are such GIS tools applicable to differentiate between old and young forest cover and their relevance in a country? That's a really challenging question, primarily because the way remote sensing works is that with the satellite imagery is that there really has to be a spectral difference between old and young forest cover, and sometimes there can be. So if old forest cover is higher density than young forest cover, then it's possible that you could sort of separate that out. But generally, it's really difficult to do a land cover classification that differentiates between those two, unless you have either spectral differences between them, or you can separate them by some other means, whether that's sort of elevation, or it's some kind of climatic variable that you can use to separate them out. Oh yeah, somebody mentioned a training topic could be point clouds. So LiDAR data would be an interesting thing to look at as well. Oh, somebody mentioned something called Saga GIS. So I am not familiar with Saga GIS. Maybe that's something we have to look into. So Carlos has a very interesting and long question. I'm just going to read it to you all. I want to assess the connectivity between some protected areas in the northeastern Cordillera of, I'm sorry, I'm crushing the language, of Colombia what will we have seen till now and what we surely will learn through the sessions can be really useful. There's more questions coming. To determine an accurate way the functional and structural connectivity. However, taking into account my background and the questions and answer posted in today's session, the available information is based on the standards or goal that each country wants to achieve. That's correct. Could this fact represent a difficulty for me? I would say not, Carlos, not necessarily. So connectivity is something that a lot of people are trying to sort of get at in various countries. And if you may want to email me, and I can tell you about some specific projects that are going on looking at connectivity, even in Colombia, that you may be of interest. So why don't you, if you can, give me an email and I will send you that information. All right, everyone. At this point, it's time to end the webinar. I see more questions coming, but if you have questions that you would really like answered, I recommend that you email us. I'm putting our email addresses back on the screen now in case you need them again, and we'll try to do that this week. We'll be on again tomorrow, so hopefully we can answer more questions tomorrow, but we appreciate you attending. And we hope we see you again tomorrow. Thanks, everyone.